What's up, peoples? So today we are going to talk about transport. And so when we talk about transport, we're talking about things coming across a membrane. So you can be two types of transport, and I like to kind of like see this as a concept map in my head. So I'll show you a picture of that in just a second. But there is passive transport and there is active transport. And in passive transport, we have no energy required. We have high to low concentration. We go with the gradient. This is talking about like the flow of particles, where particles are located. We also have active transport, which does require energy. It goes from low to high concentration. So we're going against this natural gradient of where all the particles are located. And so when we talk about low to high, when we talk about against the gradient, we're talking about both sides of the cellular membrane. Okay, so if we have like a lot of particles up here, that's the high concentration. And on the inside of the cell, we might have very few particles. That would be the low concentration. So types for passive include diffusion. And diffusion can be dialysis diffusion or it can be osmosis diffusion. And then we also have facilitated diffusion. Types that are active transport are endocytosis, which include phagocytosis and pinocytosis. There's exocytosis, and then there's sodium and potassium pumps. Okay, so here's what this looks like in my head as a concept map. Obviously, you've got active, you've got passive, you've got three different types over here, and then the subtypes of endocytosis. You've got the types over here for passive, and so we learned that the cell membrane, it says, hey, no go if you are a charged particle or if you are a large particle. And so we have things like active transport, which help us move large and charged particles. So like a sodium potassium pump is really, really good at moving charged particles like sodium and potassium. We also have like exocytosis, which pushes stuff out of the cell that requires energy. We also have endocytosis, which is bringing stuff into the cell and also requires energy. And you can have pinocytosis, which is like a cell is kind of like drinking, so these are typically liquid type things. You can also have phagocytosis, which we're going to bring it in to the cell. We're going to engulf it, requiring energy, and a lysosome is going to break it down for us. Okay. In passive transport, like we said, we have our dialysis, and this is going straight through the phospholipid bilayer. These are typically particles that are small. These are uncharged particles, and they can just diffuse straight through the cell membrane. We also have osmosis, which is only limited to diffusion of water. Okay, so we have three types of osmosis. There's hypotonic, isotonic, and hypertonic. And we talk about that a lot later. We are going to be pros at osmosis by the time we are done with this unit. So I don't want to harp on it too much right now. And then we have facilitated diffusion. Now, the big difference here is in diffusion, we're going straight through the phospholipid bilayer. In facilitated diffusion, we are moving a large or a charged particle, still with the gradient, okay, still going from a high to a low concentration, still requiring no energy, but these guys need a transport protein, which is why it is called facilitated diffusion, because a protein will facilitate the diffusion across the membrane. All right, so let's talk really quickly about active transport. Active transport does require free energy. It means it requires ATP as an energy source. And what we're doing is we're moving particles from a low concentration to a high concentration, which is the opposite of where the particles want to be. Okay, so particles, and when we talk about water and when we talk about particles and we talk about concentrations of things, they like to balance each other out. We want the same amount on the inside and the outside of the cell. That's how they naturally want to kind of operate. Well, in active, we don't want that same concentration. We want one concentration to be higher. We want one concentration to be lower. So we're constantly going to try and push things out towards a higher concentration so that we build up concentration. So that's active transport. And again, the type of energy that it's using is ATP. And it has to use proteins that are embedded in the membrane to move these. It typically doesn't do it by itself. We definitely need those membrane proteins. They have to be there for active transport. So here is our quick little comparison. Again, this is that concentration stuff that I was talking about. Here are these particles in passive, and these guys, they want to balance out. So they're going to just move from high concentrations to low concentrations, and once they're balanced out, they can kind of stop the process. However, in active transport, okay, you can see our energy required for this protein, and we've got these little guys that we want to keep them in the cell. We want to build up a concentration of these little diamond particles. And so we're going to use this protein with some energy to grab these guys and move them into the cell so that we can go against the gradient. We require energy for this. We go from a low concentration to a high concentration. So one example of active transport also on your concept map is the sodium-potassium pump. Okay, so here's one really cool thing about the sodium-potassium pump. This one is really, really important for when we talk about electrochemical impulses. So you may have heard of the word impulse before. You may have seen it when you talk about neurons, and we're talking about like actually making reactions happen. So the sodium potassium pump is huge for our membrane action potential. It's huge for our electrochemical impulses. Okay, so one of the things with the sodium potassium pump is that, remember, this is active, so this is a process that requires energy, and you can see that ATP is kind of our driving force here. As soon as we put ATP in, the membrane's going to get to work and it's going to do what it's supposed to. Okay, so the binding of the cytoplasmic sodium to the protein stimulates phosphorylation of ATP. And the fancy word phosphorylation is just basically we're taking a phosphate off of ATP, which stands for adenosine triphosphate, and we're turning it into ADP, adenosine diphosphate. We talk about this a little bit later. So I'm not going to get too in-depth into it, but that's just the fancy thing that phosphorylation means, is that we're dealing with one of those extra phosphates. Okay, so this is actually what's going to cause the protein to get into action, so that we can actually remove those sodiums. Okay, now all that is happening, and then at the same time, okay, what we're going to do is we're going to have some potassium attach to our protein on the opposite side, so a different type of protein conformation. Okay, and when we pull off this phosphate, that can go and reattach to an ADP to create ATP again. We're going to take those potassiums and we're going to move them into the cell. Okay, so one of the things that we talk about when we talk about our sodium potassium pump is that it's actually building up a charge, and that charge is going to be what triggers our neuron impulses, our electrochemical signals for us. So we can see this like membrane uneven charge between our sodiums and our potassium. We shoot those out and we build up that charge and then fire them to actually give us our electrochemical impulses. Okay, and we'll revisit this topic when we do the neuron system. So don't stress about it too much, but for the purposes of this, it's an active form of transport. The ATP, the energy, is triggering and a protein conformation to help us build up an electrochemical gradient. So we talked about the membrane potential on that, and we talked about it being an electrochemical gradient. Okay, so what we're doing when we're moving those charged particles through the membrane is we're actually creating a voltage difference. Okay, so the voltage is created because of the distribution of different positive and negative ions. Okay, so this actually creates us an electrochemical gradient, or an electrochemical distribution that drives the diffusion of those ions. And when we say drives the diffusion of the ions, it's like that they're going to build up so much that they fire all at the same time and create that electrochemical pulse. This is a chemical force because the ions are the concentration gradient, so they are on a sodium and they are on a potassium. This is an electrical force because there is this charge on those ions that builds us a membrane potential. Okay, so again, we have other types of pumps. This is an electrogenic pump. Again, same concept. We're going to build up a voltage across the membrane. So here you can see we are actively pushing positive hydrogens out, building up something called a proton gradient, which we're going to see this when we talk about energy. So it's important that you kind of have an idea of what's going on here. So we have this huge unequal sharing of charge. We have a bunch of negative charge on this side, a bunch of positive charge on this side, and we're creating this unequal sharing of electrons. This is done by a special protein called a proton pump. Okay, and we have these pumps in plants, we have these in fungi, we have these in bacteria. A lot of the things that are autotrophic are going to need these for sure, but we also have them in mitochondria. And co-transport. Now, this is the one that we like to talk about a lot as well. We have co-transport, which is a proton pump, triggers a second protein to allow for some sort of active transport. Okay, so this proton pump is the only one that's actually getting energy, but the reason we're doing it is so that we can send a positive charge to help us and allow us to bring in a larger molecule. So this is actually the signal that pulls in very large molecules. And so the sucrose is the co-transporter. The sucrose H plus is the co-transporter. So until it gets a signal from this positive hydrogen, it's not going to know to bring in this sucrose or have the ability to bring in this sucrose. And so this is like an indirect type of transport. It's complicated in the fact that the energy is required for this one, but unless A happens, B cannot happen. So these are common also in plants. These are used as a gradient of hydrogen ions generated by protein pumps, and these drive active transports or nutrients coming into the cell. So we'll see these in plants a lot of times as they kind of suck in different nutrients that might be really, really large and hard to get into the cell. We will also see something that looks very similar to this when we talk about the mitochondria, that this proton pump is actually generating this gradient to allow something called ATP synthase to actually create ATP. So that's a little preview of something that's coming next unit. Okay. All right. So the other things with active transport are endocytosis and exocytosis. So endocytosis, pretty obviously we're going into the cell, okay? Endocytosis, endo into, cytosis means cell. And we also have exocytosis. Exo means exit, cytosis, cell. And so whenever we don't know things, we want to break apart the words so that we kind of get at least a base understanding of what they are. And so with endo and exocytosis, we are moving just massively large molecules. I'm talking so large that they don't even really fit through a protein or a transport protein. So we're going to do these crazy processes in which we have to engulf them and eat them up to bring them into the cell or to help them leave the cell. So we've seen this before when we have to move things through a cell or when we have to take things in, it actually forms these things called vesicles. And remember, vesicles have their own little lipid layer around the molecules, and that lipid layer holds them nice and safe. And the cool thing about this is it's very similar to a bubble. You can actually cut a bubble and it'll still be able to like operate. And so a vesicle will actually take parts of that phospholipid bilayer and then create the vesicle around the thing that it needs to engulf. And then we can like break it down with the lysosome. This is active transport because it requires a lot of energy to flex that membrane out and actually deal with it, okay? And actually make a vesicle to move and transport things in bulk that are very large like this does require energy, and it's supplied to the ER so that it can actually make the vesicle, okay? So for instance, exocytosis, you're going to see this in a lot of these things called excretory cells or secretory cells. These are cells that need to get things out, okay? So like, examples for humans, we have oils on our skin. So skin cells have these oils, and so they have sebaceous glands that need to export oils. And so that would be an example of exocytosis, that we are exporting products all the way outside of the cell. And so again, we have to get energy for this in the ER. Okay, we're going to make the vesicle itself, and we're going to encapsulate whatever we're trying to transport out, and we're going to ship it through the cytoplasm, where we can, export it and secrete it. So here's our little example. Here's our vesicle. It's holding the product that needs to be excreted, and then cool and awesome of phospholipids that they are generally attracted this way. As they kind of join to the cell membrane, they attach and then they release their product. Okay. Endocytosis. Okay, so with endocytosis, this is like a cell eating or drinking. And so in endocytosis, again, same concept. We're forming a vesicle, but the lipid bilayer is engulfing that thing and creating the vesicle. So endocytosis is the reverse of exocytosis. We're taking parts of that phospholipid bilayer to create our vesicle that's going to now live on the inside of our cell, instead of adding to that phospholipid bilayer and exporting things. Okay, so we have phagocytosis, which is a cell eating. We have penocytosis, which is a cell drinking. And then our last one is receptor-mediated endocytosis. And that one is kind of similar to co-transport, where we have to have A happen before B can actually happen. So phagocytosis and penocytosis. Phagocytosis is like a cell eating. It's going to engulf particles of food. So these are larger macromolecules. And in penocytosis, these are typically fluid-like particles, and it's going to create tiny, tiny vesicles to hold it. And then we said that receptor-mediated endocytosis is, first we have to bind to something called a ligand, and the ligand is just a fancy word for the signal itself. And that signal, or that ligand, is what is going to trigger the vesicle formation to actually bring stuff in. Okay, so again, a ligand is just any molecule that binds to a receptor site so that the molecule can actually know to be engulfed. So let's look at them. Here we have phagocytosis. We had food here. We engulfed it with our cell membrane. We took parts of that cell membrane, the phospholipid bilayer, to create a vesicle, and now we've got a food vacuole. This little food vacuole is going to get digested by a lysosome. Okay, same thing here, but this time it's a little bit smaller of a vesicle because these are liquid particles. This is penocytosis. Small vesicle, dealt with typically with a lysosome. And then last but not least, receptor mediated. On the outside of the cell, we've got these receptor, these are sometimes proteins. So this receptor protein, this is sometimes a carbohydrate chain, which is helping with cell signaling. Okay, and it will bind once it is bound to by a particular ligand or a signal. It engulfs whatever particles are around it, and now we have this nice little vesicle ready to be dealt with. Okay, so unless A happens, the binding of a ligand, B cannot happen, the actual endocytosis. Okay, all right, I'm going to do a quick overview of passive transport, but then we have to dig into osmosis in a completely separate one. Okay, so we have passive transport, which is where we're diffusing things across a semi-permeable membrane. And so this again is a passive, as in it does not require energy. This is probably going to happen either way. This is just trying to level out and equal out the concentration of particles. Okay, so there is diffusion, which is the tendency of molecules to spread out evenly, and it has different forms. Okay, so one thing I want to keep in mind as you're going through this is once we're equal, things don't just stop moving. Okay, they enter this thing called dynamic equilibrium. Okay, so with dynamic equilibrium, the particles are always in constant motion, but they're pretty equal. So we'll have one exit and one enter and one enter and one exit, and so they're still just kind of moving every once in a while. Okay, so we have high concentration here, low concentration here, diffusion across the membrane until those things equal out and enter dynamic equilibrium. Okay, this is diffusion of a solute. Okay, so this solute has to be small enough and it has to be uncharged so that it actually can diffuse across that membrane. Okay, we also have diffusion of two solutes. Okay, so we can see the same thing happening. It's specific to the solute type. Okay, so you can see that right here they're kind of equal in regards to here's the orange and here's the blue or the purple particles. Okay, so they're semi-equal already, but we don't like that. We want equal for each particle type. Okay, so you'll see the orange will start to diffuse this way with a net diffusion over towards this side of the membrane, and then the purple will start to diffuse the other direction with a net diffusion opposite of that. So until those two particles are each equaled out, we're not going to be able to enter dynamic equilibrium. Again, what do we know about these particles? They're small, they are uncharged, and that's how we get them into the in and out of the cell membrane passively. Okay, we don't need a protein for these. All right, substances that will diffuse across membrane gradients. Again, we like things that are small, we like things that are uncharged, and they like to go from high concentrations to low concentrations. This is great. This is awesome because it requires no energy, and we love things that are efficient. Okay, so let's look at diffusion in its two forms. There's dialysis diffusion. Remember, this is particles. Okay, these are small, these are uncharged particles. And then we have osmosis. This is also passive, and this is across a semi-permeable membrane, and it's from high concentrations of water to low concentrations of water. And there's multiple types of this, and we'll talk about it later. Okay, and facilitated diffusion. There's a fire drill going on, but I'm going to finish this. Facilitated diffusion is now we've got something large or charged that needs to get through the thing, through the cell membrane. So you'll see things like aquaporons, which help us with moving water at fast rates because they are polar. And then we'll see things like ion channels, which will open or close in response to a stimulus. So ions are obviously moving charged particles for us. And then we have channel proteins that just do large particles. So here's an example of a channel protein. We've got high concentration to low concentration of solute. These are too big to fit through the cell membrane. We also have carrier proteins that can be passive, high concentration to low concentration. Okay. All right. We're going to talk about osmosis later. Sorry I sped through the last little bit. You guys are awesome. Have a great day.